This is a Spyderco Nilakka, which is sort of a folding puko. Before I talk much about this knife and a couple of rather simple experiments I did in regards to practical or functional level of edge durability, I want to make a comment or reference to Spyderco and an appreciation or respect of the extreme stance that they took with this knife. Because as you can see, it has a full flat grind with no secondary edge bevel. Now, for quite some time, a lot of people have been demanding more extreme geometries. So even though you take a knife like the Temperance 2, which has a full flat grind and has a significant secondary edge bevel, and people will be asking for to thin the edge bevel down, reduce the angle, etc. to increase the cutting ability. And on the extreme end of that, you have some of the more well-known makers like Phil Wilson, who's known for doing full flat grinds, relatively thin stock, and edge bevels which are typically in the range of 5 to 10 thousandths and edge angles of around 15 degrees per side. There's also quite a number of YouTube makers who run very thin edge bevels. This is a knife from Michael Gavko. It's a Spartan. And it has a full convex grind, and it had a bit of a secondary transition, but I took that out because I didn't need that level of durability. So right now it has a full convex blend from spine to tip with no essentially secondary edge bevel, just a full blend. And you can get the full specifications on this, the exact angles and such that I use in other videos. Here's another example. It's a blade from Dan Keffler, which I had custom made. The edge on this drifts down to around 5 thousandths near the handle. It sweeps up to around 25 in the main chopping section and went down to around 15 in the tip. And it was very extreme for a knife of this size. This is a rather large and not lightweight blade. And it brings up the question, of course, of functional durability and limits and responsibility of the maker or manufacturer. If someone uses this beyond its scope or intended purpose, the actual primary grind could get damaged, not just the edge. Or if it's sent to somebody with not a proper level of skill or understanding. And that's the problem when you mass produce blades. When you custom make blades, you make them for a particular person, you can have a conversation with them. Just like Dan had a conversation with me and said, "You really, really want that? That's a rather extreme geometry." Now, back to the Nilakka, there's already been some commentary on these as they were made, and criticisms of the extreme geometry because it did not offer a practical level of durability. And interestingly enough, right now there's a bit of an exchange, or was for the past couple of weeks, between a number of YouTube makers and personalities and commentators about issues such as edge thickness in relates to functional level of durability, like what do you actually need in regards to an edge to keep it essentially in one piece and then give the maximum level of cutting ability. Because your maximum cutting ability comes with minimal durability. It's just durable enough to keep the knife from being damaged. That's what gives you your maximum level of cutting ability. So there's some makers who take that approach. Michael Gavik and Collie Harris are examples of YouTube makers who try to make their knives just minimally durable, not overbuilding. So they have maximum cutting ability, maximum ease of resharpening, maximum ease of maintenance, that type of deal. And there's other popular makers such as Medford, who moves completely to the other end of the scale, who makes knives that are geared obviously much more towards higher level of durability. He talks about prying open car trunks and other types of deal. And there was an exchange between a number of these makers, not directly as if they were talking to each other, but implied references in some videos, which eventually led to Medford taking all his videos down and then putting them back up and turning comments off. It's a rather odd move for a maker, but regardless, his viewpoint was again more towards extreme durability. So a question that you always should have in mind when you're looking at a knife, whether it's a Spyderco Nilakka or Temperance or this Coyote Meadow from Phil Wilson, is does it have the level of durability needed for what the knife is meant to do, and more importantly, what I need the knife to do. So with the Spyderco Nilakka, I did two very simple experiments. One was to look at the ability of the tip, and again, these are very low stress experiments. Just put the tip on a piece of 1/8 inch normal ridged cardboard, spin the knife like this under its own weight, and drill through the cardboard. And as you see now, it's not drilling through the cardboard or going very slowly. There it starts to go in now. And the reason why it's going so slowly is that the first time I did it, a piece of the tip cracked off almost immediately. So now it's blunt, chisel tipped. That's relatively on the low end of durability, and it's rather extreme that you could say that very light spinning cracked off a piece of the tip. The other thing I did was just make a few slices through cardboard. The amount of force used was very minimal, so the control is very high. The comfort in hand is very high because you're exerting no force on the blade. That means the handle is exerting no force on you. However, even after the first slice, I could see light starting to reflect around the edge and more from one side to the other when I turned the blade, which meaning sections of the edge had actually collapsed just from the few cuts. So the edge retention was essentially zero because the sharpness went from very high to essentially nothing. So this section of the blade is blunted now. It has very little sharpness where it's rolled, and you can feel roughness in it where the edge is back and forth. And in the pictures, and I even put up a video that I took along the edge at 50 times magnification, you can see down here, which wasn't used to cut, how the edge still has a very crisp micro bevel, which was put on probably by a buffer, and then as you move up into the section which cut the cardboard, the edge starts to dip and roll and wave, and that's where it's collapsed from the cardboard cutting. And again, it's a very low level of durability. So it didn't have the durability to even drill through the cardboard, didn't have the durability to slice through the cardboard. So excellent cutting ability, very, very low durability. So you'd have to question right away, what's the practical function or scope of work for this one that can't handle that type work. Now, this is where I'm going to get a bit scientific for a few minutes. And for some reason, a lot of people react to that term as if it's some sort of kryptonite. All scientific means, if you're trying to be scientific, all it means is that you are trying to form a conclusion which is based on observation and rational thought. That's all it means. The opposite of that is when you have an opinion. And an opinion is not based on facts. It's not based on knowledge. It's based on the fact that you hold that viewpoint or belief because it makes you happy, because you like to have that viewpoint. And again, that's the difference between a scientific viewpoint and a viewpoint based on opinion. The other central difference is that opinions can't be falsified. There's no way to say if an opinion is true or false. If you have a scientific viewpoint, by definition, it has to be able to be true or false. Now, you can hold scientific viewpoints which are turned out to be false. And again, that's a critical difference. Simply because you say, okay, I have this view and it's grounded in science, doesn't mean that it's right. Scientists are wrong lots of times. That doesn't make them not scientists. So again, that's the difference. So I'm going to be a bit scientific for a few minutes. The critical question to look at is, why did the Nilikka fail? How come the tip broke off immediately drilling in a bit of cardboard? How come the edge collapsed and rolled and got this wavy sort of feature and the edge retention went to zero in this area right here immediately on cutting through cardboard? But yet you can take, and I've shown in many other videos, a very inexpensive knife out of, say, 420 J2 stainless and cut up hundreds of meters of cardboard and still have enough edge retention to easily slice paper, no visible chipping, denting, rolling. A few ideas are immediately tossed out. People claim, oh, it's S30V and S30V is inherently too brittle. Or there's something wrong with the heat treatment of the blade. Or the blade is ground much too thin and a blade this thin can't be used to cut cardboard. Ideas are just tossed out. So if you were to look at this from a scientific viewpoint to try to come up with a conclusion, how do you do that? The first thing you have to do is look at all possible causes, not just the ones that you like. You have to look at all possible causes which could cause it, and then you have to see which ones of those are true. So you have to come up with a way to test them to see if they are true and false. Now when you're doing that, in general, you write down all the possible ways that it could be, and then you start with the ones that are very easy to test, because you can very quickly weed out if they're the true or false ones. So one of the ones which would be very difficult to test would be, well, what about if this blade was overheated and the grains blew up and got extremely large, and then it was quenched too slowly, so precipitates started to form, and then it was tempered too far or too long after the quench, so then you got micro cracking in the steel and stabilization of austenite. Then you'd have a blade which would be expected to perform like this. The hardness would be too low, but the blade would be too brittle, so you'd end up with a blade that rolled and chipped at the same time far more than what you would expect out of the steel. So that's a possible explanation which fits the observations. However, it's very difficult to test that. You would have to take this blade, polish it, etch it, and look at it under very high magnification to look at the microstructure. Very costly unless you have the specific equipment. And it's also probably unlikely that Spyderco would do all of those things wrong while heat treating the blade. So a more likely explanation, which is very easy to test, is, well, what about if the edge just got overheated when they were grinding it, and then someone dipped it in water to cool it down? These are very common practices, and it's not that unheard of to happen. Well, in that case, the overheating would make the edge of the blade softer. It would make it weaker. The violent dipping in water would cause micro cracking, so it would make the blade more brittle. So if that happened, you would expect the edge of the blade to be weaker and roll and deform and also experience fracture, like we saw at the tip. So that's an explanation which also explains the observations, but it's much easier to check. All I have to do is take this, grind the flat on the edge of the blade using an abrasive, which is cooled, so I remove the heat damaged section of the blade. Then I plane down the flats to again come to this zero edge, and again put that very, very microscopic, true micro bevel on the blade and repeat the cutting. If I find there's even the tiniest hint of improvement, that's support for my conclusion. So I would do that a couple of times more and see, am I getting significant improvement? And if that's the case, it's most likely the fact that that's what's causing it. As I've shown before in many other videos, it's relatively common for edges to come with that damaged edge. And then when you just sharpen it using proper tools and proper methodology, you can move back into quality steel and the edge gets much more stable, it gets much more durable, it gets much more easier to sharpen because you're again on quality steel. This is Spyderco Nilakka after the first sharpening session. So the first thing I did was take a 1000 grit water stone and cut straight into the edge for 2 passes. Now that does 2 things. Number 1, of course, it grinds off all that deformed, weakened, and chipped metal. You don't want to try to sharpen that. The second thing it does is it leaves a flat along the edge, clearly reflecting light. That I can use to very easily tell when I'm sharpening once I reach the actual apex. So then with the 1000 grit stone, I plane down the entire flat of the knife, the actual primary bevel, until it apexed and was no longer reflecting light. When I did that, I saw pretty much what I expected. There was a huge burr along the edge, that big that it was clearly visible by eye. And I'll show some magnification shots in the corner of the video, and you can see it's huge. These are 50 times magnification. Then I tried to remove that burr by putting the knife on a huge angle to the stone, up to 45 degrees, but it wouldn't cut off. It just flopped back from side to side. Again, that's sort of what I expected. I went to a 3000 grit stone, and again, cut straight into the edge to grind off that weakened metal, that burr. Then again, plane down the flats with the 3000 grit stone, and this time the edge formed clean. Then I applied a very tiny micro bevel with the 3000 grit stone. Then I took an 8000 grit stone, planed down the flats again to remove that tiny micro bevel, and just did 1 pass per side on the 8000 grit stone. And again, this is a micro bevel, you can't see it, and even under magnification, a 50 times magnification shot, you will barely see any hint of a micro bevel. So now it's back to the same geometry that it was as boxed, except with a couple of modifications. Planing down the primary grind has smoothed out those scratches, and you can see as you get close to the edge, it's starting to pick up that mirror polish because the scratches have been heavily removed. So now it's a much finer polish than it was as boxed. But more importantly, it was all done slowly, hand sharpened, and water cooled, so there's no ability for heat damage or mechanical deformation at the edge. Did some checks on this, sliced through some rather soft materials, cardboard and the like, no issues, the edge is holding up just fine. So now, it's time to do a series of experiments and move through various materials and see what are the limits of this edge where you start getting deformation due to essentially the geometry alone. Because now I've sort of moved past the steel issue and now I can look at the geometry. So it'll be rather interesting now to use this knife.